Good afternoon. This is Kyle Welch with RCR Wireless News. I want to thank you for attending RF interference hunting techniques presented by Anritsu. Our presenters today are Tom Elliott, Senior Product Manager at Anritsu, and helping him out with the Q&A section will be Steve Thomas, Senior Product Manager at Anritsu. Just a reminder to all of our attendees that within 24 hours of this webinar, we will provide you with a link to the on-demand version of today's webinar. During the webinar, we encourage everyone to submit questions via the control panel, which will then be answered at the end of the presentation. With that being said, I'd like to turn the presentation over to Tom.
Hi there. As Kyle mentioned, I'm Tom Elliott, and welcome to the seminar on RF interference hunting techniques by Anritsu. Here we'll talk about ways to spot, find, and fix interference. So the first question that always comes to my mind is this problem interference? Do I have interference? Or is it something else? So what am I looking for if I'm going to decide that this is interference? First thing I want to keep in mind is the frequency bands are crowded and they're getting more crowded. If you go through the numbers, you wind up with 5,000 licensed radio transmitters in Santa Clara County and over 500 within a mile of the Anritsu headquarters in Morgan Hill, California. When you start including mobile licenses in the county, we have over 12,000. And this doesn't include cell phone users. It doesn't include Wi-Fi, government users, FRS radios. It doesn't include police, fire, mobile, and handheld individual radios. There's a lot of transmitters out there, and the number is growing daily. Not only that, all the new emphasis on digital transmissions, LTE and 4G, is placing much more severe demands on the spectrums we do have, and interference tends to lower the data handling capability of any piece of spectrum. So interference is becoming more of a problem than it's been in the past. The first indicators of interference, if you have an analog link, is noise. You've all heard the hiss and the noise and the sputs and the pops that you can hear when there's interference. In digital transmissions, it's a little different. We get low throughput. You may have heard on your cell phone that waterfall sound when you have a weak signal and the call's about to drop. And of course, a high drop call rate. A second indicator, a more technical indicator for interference for both two-way and cellular, is a high receiving noise floor on a specific receiver or a specific sector. We'll be talking a lot about that as we go through here. For broadcast, we're talking about customer complaints. Any one of these indicators is enough to warrant an interference hunt. It also identifies the geographic starting point for the interference hunt. So for cellular systems, there's one thing we can try. If your interference signal is strong enough to be seen from more than one sector, is you can check power levels of the RSSI level in the various sectors. You can see I've got sort of an oversimplified model of a cell antenna here with 3 sectors, and there's, of course, other cell antennas adjacent to this. If you start checking RSSI levels, it can give you sort of a rough idea of where the interference might be coming from. Unfortunately, not all interference is strong enough to be seen from more than one sector, but if it is, this is certainly a way to give you a clue. Okay? If you're in a broadcast system or a point-to-multipoint, such as the emergency services system, you get into something called the near-far issue. And this is where your tower has a wide range of coverage, and out towards the edge of your tower's coverage area, there's a bunch of cell phone towers. If they happen to be close enough to your frequency that your fireman's receiver, his two-way radio, can pick this up, the cell phone frequency as well as your frequency is going to desensitize the emergency services radio. We'll talk about that a little bit more, but there's a point I want to make here, is that an interfering signal does not have to be on your channel to be interference. Okay? So let's talk a little bit about spotting and characterizing interference. Now that we know when we're looking at interference, in other words, we have receive problems, let's take a look at what we might see when we hook up to the receiver's test port. Okay? Interference at its heart is a receive issue. You can argue that a strong interference can interfere with a downlink signal, but in the end, it's the receiver that's affected. So the best place to start looking is at a receiver. If it's on a cellular uplink, start looking at the tower. If it's on two-way radio, again, start looking at either the receiver for the complaint area, if it's with a handheld, or at the tower if it's hitting everybody. If it's broadcast, of course, we have to go out to where the receivers are, the TV set or the radio or whatever it is. The important thing now is to measure the noise floor, if at all possible, from a receive antenna, because that receive antenna has the same height, visibility, and pattern as a radio. And I'll tell you right now, especially on a cellular system or two-way radio system, a signal that you can pick up quite easily when you check the test port, as you've shown here in the diagram, can be a lot harder to pick up at ground level. So a lot of what we're going to talk about is how to make sure we know where, when, and how our signal's occurring using the antenna that can see it before we can switch over to the ground level antenna. So it's important to get a visual idea on the interfering signal to characterize the signal so you know it later when you're having difficulty seeing it from the ground level. So interference is a receive issue, and I want to point out that we need to be looking on the receive frequencies for interference, not on the downlink frequencies, on the uplink frequencies if we're dealing with a cellular tower. So we have a little diagram down here, and the gray area represents the band of the receiver we've got here. The blue lines represent the filter response of the pre-selector or the pre-filter. The yellow is our receive channel, and the orange is the interference. Now you notice the interference is not on the receive channel here, but it's still getting past the pre-selector, it's still getting into the front of the radio, and it's still counted as total power by the rather wideband front end of the radio. And it'll tend to reduce the sensitivity of the radio. This mechanism is called receiver desense or receiver desensitization. If it's very severe, it can even be called receiver blocking. But I want to say it again. Interference signals do not need to be on your receive channel. They only need to make it through the receive filter. Okay, so once we see a signal that could be interference, we want to spot these strong signals on the receive band. A dual trace spectrum can help us see what's happening. In the upper left of the screen here, you see a max hold and a normal trace. I use this a lot when I'm hunting interference. The normal trace lets me see what's happening right now, and the max hold trace lets me see how bad it's gotten ever. And especially if I've got a Yagi in my hand and I'm moving around or something, watching the normal hold trace getting close to the max hold trace helps me know when I'm pointing at the strongest signal. And if I've got something that pops up once in a while, it helps me keep an eye on where it is. We can also create an auto mask off this max hold trace and do a save on event. Some of the hardest signals to find are the ones that come and go according to some sort of a pattern over time. And if we generate a save on event mask, an upper limit if you will, when they save, they're saved with time marks. And so we can look at those time marks in the file name and start getting an idea of just when this signal occurs. Of course, there's a spectrogram over here, which is a very useful tool for any sort of signal that's changing in frequency or changing in time. You can see here it's been used on some FSK signals, and it becomes very obvious they're FSK when you're looking at this plot. Something that I find very useful and I strongly recommend is know what's in your receive bands. Know which signals belong and know which signals don't belong. It really helps. It speeds things up no end to be familiar with what you should be seeing out there. Also, another tip is allow the receive pre-filter to eliminate signals. If they don't get through the receive pre-filter, they don't get to your receiver, they aren't causing desense, they aren't a problem, okay? If it's not possible to get into a test port off a receive pre-filter, you'll just have to ignore the signals you know the filter will eliminate. Now, another point here, if you're hunting for an interfering signal and you don't have a receive pre-filter on your receiver, it's probably time to get one. Okay, so here's a sketch of some RF interference. I saw this at a site out in St. Louis one day. The pale apricot color, I guess you'd call it, has to represent the receive band, and specifically is representing what the receive pre-filter is allowing to pass through. You can see where the WCDMA uplink should be. This is a representative sketch of a max hold waveform. There was a GSM uplink that was showing up once in a while over to the left there. On the right, there's a very strong signal that was always there. This is a few years ago, and that was an IDEN signal from a tower that was maybe 200, 300 feet away from the tower we were looking at. The reason I'm bringing this up is we've got a strong signal in the receive band. It's not on the receive channel, but it's in the receive band, and it was totally desensing the receiver. The technician that had been working on this problem saw this. He'd been working on this for 6 months, but since it wasn't on his received band, his received channel, excuse me, he didn't think it was a problem. And as soon as we adjusted the filtering to take care of this, of course, the problem went away. So again, interference doesn't need to be on your channel, it only needs to be in your receive band. Along the way of knowing your bands, it's worthwhile to take a day or so to develop a library of the signals you expect to see in your receive bands for your area. These are some signals I picked up in Portland, Oregon in an afternoon one day. I was looking at what was out there in a variety of bands and also using the FCC database to help identify things. So the first one we have is the 7 CDMA carrier signature that's common to Verizon transmissions in the US. 7 times 1.25 megahertz should come out to the bandwidth of the signal you're seeing up there. Go down a step and you have a single carrier, which is 1.25 megahertz wide, so it's either CDMA or EVDO. Okay. That's multiples of this again. The third one down is the new FM digital transmissions around 100 megahertz, and finally the lowest one is a P25 signal with its 12.5 kilohertz bandwidth. And you know, all these signals have their own distinct shape. They have their own distinct signature, if you will, on the spectrum analyzer. It's well worth the time to go through your frequency bands and get a handle on what's supposed to be out there. That way you'll know what's right and what's not right. And things that are not what you expect stick out like a sore thumb. The quickest way to identify a signal, going with this library theme, is visually recognizing the signal. If you say, oh yeah, that's a CDMA signal at this frequency, I happen to know that that belongs to such and such transmitter, or such and such a network operator at least, that gives you a good start towards knowing what you're looking at. So visual recognition is important. Keeping a bunch of, yeah, that frequency and that bandwidth and that shape belongs to this guy in your head or written down somewhere is very helpful. So know your signals and know your frequencies. If we're dealing with an analog or a digital signal, oftentimes we can demodulate it if the signal's in good shape. We'll talk about that a bit more on the next slide. And after that, the next step is the FCC licensing database if you're in the US, if you're in Canada or some other countries. Many countries have their own licensing database. Some people consider it a government secret and don't publish it, and some countries make it publicly available. Okay, in the US there is the FCC database. There's a link to it here. The caution is this database tends to be out of date. It's updated on a somewhat voluntary basis, and people tend to not pay a lot of attention to it. But on to signal demodulation, and I'm going to make a assumption here that the interference signal is in good shape. That is, it's not a product of intermodulation distortion. It's not a 15th harmonic or something like that. If it's in good enough shape that we can demodulate it and understand the message, it can be helpful to try a demod. AM/FM demod, you can listen for a call sign, paging signals. Buried in all that hiss and sputter and hum they have when you're listening to them in the FM, they also have a Morse code call signal that comes out. A call sign, I should say. And you can pick that out. If you know Morse code, great. And if you don't know Morse code, you can at least write the dots and dashes down and look it up later or using Google. Cellular signals. You can often find a scanner. I know most of the Anritsu equipment has scanners for the variety of cellular equipment out there, or the cellular standards. You get things like the cell ID, the group ID, and the sector ID of the signal we're dealing with. And this can be a great help, especially if you're trying to debug something in your own cellular system. Say you're getting unintentional coverage. A scanner of this sort can be a great assistance. Now we're still hooked up to the receive test port in this scenario I'm going through, and we're still picking up a signal from the receive antenna on top of the tower. Now's the time, assuming that none of our shortcut methods work to identify it, that we need to take the next step and characterize this signal. We need to recognize a signal later when we see it in an unfamiliar application, so we need to get used to the frequency, the bandwidth, the shape of it, the power levels that we're seeing, and any time-based characteristics. And time-based characteristics can be a real big one when we're hunting for a signal like this. There's a lot of clues, a lot of frustration, and a lot of opportunity in how an interfering signal behaves over time. We can also use things like the automask to look for intermittent signals on or near a legitimate signal. As I mentioned briefly before, this can save traces when the mask is violated. And this, by looking at the timing of the violations, you can get a good feel for what time of day. See if there's any, hey, at rush hour every morning and evening this happens. Or this happens every day at lunch, or it happens on work days, or it doesn't happen on weekends, things like that. It'll give you clues. And these upper and lower masks can be created automatically on the instrument. You're looking for unusual events, things that will violate these masks. Spectrogram, in this case, is being used to look at a signal that changes over time. This particular signal was from a cell phone booster with insufficient isolation between the input and the output. It's consumer-grade equipment. Somebody brought a cell phone booster, put it on their house, didn't really install it right, and you're probably wondering why they still have bad cell phone coverage. It's a common issue with consumer-grade equipment. And if it starts giving itself feedback, it'll oscillate. This oscillation can be temperature sensitive. It can also be sensitive to changing reflections. People walking by, cars driving by, things of that nature. It can cause this thing to burst out into oscillations. The primary signature here, though, is when you see it. Look at what it's doing in frequency over time. That's just a characteristic of a drifting, oscillating signal. Okay. So as I mentioned before, signals can occur at specific times of the day or days of the week. One thing I ran into, it was a gas station. You've probably seen those little satellite antennas they have on the roof. What they use those for is to send in their receipts at the end of every 24-hour period. And this particular one, the transmitter on that satellite uplink had gone bad, and it was transmitting at a very wide range of frequencies, including on top of a sheriff's dispatch. So in this case, in Washington County, Oregon, every afternoon from 3 o'clock to 3:05, the dispatcher couldn't send any police car. The police station was being shut down every afternoon between 3 and 3:05 by the guy at the gas station who was sending in his day's receipts. He had a bad transmitter on his satellite uplink. I also heard a story about a car with a jammer in it. This particular fellow had decided that He didn't want anybody driving near him using their cell phone, so he put a jammer in his car. And what it did was every weekday from about 8 o'clock in the morning till 5 in the afternoon, it shut down the cell where this guy worked. He probably wondered why he didn't have any cell phone service at work. I've heard of a story where a teacher wanted to. In this case, he had a jammer in his desk drawer, and he'd turn this on during tests, and it would bring down cell phone service for that sector. I've heard of meeting leaders who don't want interruptions, shop owners that don't want their employees on the cell phones. Twice I've run into a situation where a guy in an RF lab was testing new circuits that was bringing down nearby cell phones. You'd think that would be rare, but twice. And finally, here's one that's a bit of a kicker. Base stations adjust their power depending on loading, and they tend to breathe, bloom, or grow during rush hour when they're loaded to capacity. So characterizing interference by time of occurrence can give you some good clues. It's sort of like you're a detective trying to figure out where this problem is. Also, characterizing them by time of occurrence is very important if you're sitting there going, well, when do I look for this signal? I drove all the way out to this site and nothing's there. Well, maybe you went out at the wrong time and you need to pay a little more attention to when the signal happens. Okay, characterizing signals by external events is also important. What you see here is a picture of a cruise ship by the name of the Norwegian Star. There's a situation a few years ago, whenever it would dock in Seattle, it would shut down the GSM cell phone service in every nearby cell site around the dock in Seattle. Well, the problem is the US cell phone service has a 1900 megahertz downlink and an 1800 megahertz uplink. This ship has a decked phone system set up on the European standards. It uses 1800 megahertz for an uplink. Their uplink, our downlink, that's not a good combination. Whenever that thing would dock in Seattle, the cell phone service would go down on that sector. Navy ships down in San Diego, they tend to come into port and leave some of their high-powered radars on, and they'll shut down cell services in that area of the city. Signals may occur on certain work days. I've seen problems when a karaoke bar opens and the wireless microphones interfere with stuff on the 700 meg band. Steve Thomas, who'll be answering your questions here later on, has seen AM radio problems caused by a bridge opening where the bridge, once it was opened, was at a resonant frequency. I've also heard of weather conditions causing interference. In this case, there is a barn roof near a repeater, and the barn was rusty, and when the wind would get gusty and blow, it would flex the metal panels on the roof of the barn. And as the panels flexed, the PIM would come and go. I have even heard in areas with lots of deciduous trees where propagation improves when leaves fall off the trees in the winters, and it goes down when the leaves come back on the trees in the spring. So look for external events. Again, you're a detective, and you're looking for whatever external event may correspond with the interference you're seeing here. Another time duration thing is interfering signals can be short, medium, or long term. There's the guy walking by with his police radio with a push-to-talk transmitter. Bridge openings, delivery trucks, interference during a meeting. As I mentioned, PIM due to a wind. It's possible that transmitter equipment could fail, or there could be a new transmitter installed somewhere. Now we're getting to a longer-term interference. Matter of fact, it's not quite an interference, but I know one guy was quite proud of finding what the problem was in a particular sector. That someone had put a new building in front of his antenna. That would be a long-term problem. Okay, and of course there's PIM that can always be on. Now here's an interesting one I heard about recently. If you take a look at the trace here, it's a very wideband trace. We're in a 20 meg span here. And the interfering signal, you can see it popping up there. You can also see times when the trace hasn't popped up. Now if you look at it, just to think of it as a spectrum trace, you think of it as sort of a picket fence. There's a series of fairly wide carriers, and there's an area where there is no carrier at all. But the clue with this particular trace is look at just how sharp it goes up and down between the carriers. The other clue is if you're watching this, what you'll see is the trace is actually sweeping rather slowly, and it's going up or down as the signal is turning on and off. So what this means to me is we've got a signal or a series of signals that are turning on and off. They're generating some very wideband splatter, which is typically PIM. And the splatter is either there or it isn't there, depending on whether the source signals are there or not. And you see the one tall signal over on the right-hand side, that's our desired uplink signal. Everything else is interference. Okay? So the key here again was looking at how the signal changed over time. It was fairly obvious it was turning on and off. Then there's bursty signals. A lot of digital signals are bursty. By bursty I mean they're on 50% of the time or less. Signals like Wi-Fi, LTE uplink, a WCDMA uplink, CDMA uplink, or Bluetooth. And it's very handy to have a burst detect mode to view these signals reliability. In this case, burst detect is a trace mode. It's a trace mode that detects signals over 200 microseconds. So how it would work is picture yourself standing out there with a spectrum analyzer in one hand and Yagi the other, and you're trying to find this signal that's just showing up once in a while. Maybe it's showing up every second or every 5 seconds, every 10 seconds. Maybe it's showing up once a minute. At any rate, it's intermittent. What's happening is your spectrum analyzer, if this is a bursty signal, if it doesn't happen to be looking at the signal frequency while the signal is turned on, it won't see it. And a spectrum analyzer sweep is not terribly fast. It tends to look at it doesn't actually look at any one frequency very much, maybe 1% of the time. Okay? In burst mode, it's looking at all the frequencies all the time. And instead of a signal that's on, say, once every 30 seconds, you have a signal that shows up every time it pulses. So maybe now you have a signal that's on 90% of the time. This makes moving that Yagi around to localize your signal much, much quicker. Burst detect is something that can save you a lot of pain. So characterizing interference, let's summarize this section on characterizing interference. It's important to know the signal frequency characteristics, the frequency signal shape characteristics, and the signal timing characteristics. This helps you know when and where to look and what you're looking for. You need to be able to recognize this signal and its behavior during the hunt. A little bit of a summary on interference generators. We have another application note called RF interference hunting techniques that talks in quite a bit of depth about various causes and mechanisms for interference. We aren't going to cover that here, but I want to leave you with this, that any signal at a receiver's input can cause descents. If it gets through the pre-selector, if it gets physically to the input connector on the receiver, it can cause descents. And there's a lot of things that can happen here. We can have on-channel interference, off-channel in-band, impulse noise, jammers, harmonics, intermodulation, or even the near-far problem. But the key point I want to leave you with is if it made it to the input of the receiver and it's not your desired signal, it's interference. Let's talk about interference hunting aids now. Okay? So far we've been hooked up to the receive test port on our tower. Signals that are strong at the tower level can be weak at the ground level. There may be hills, there may be buildings between you on the ground level and the source of the signal. So I've already mentioned that you can check other receivers for interfering signal strength to get a general idea of location. You can also drive around and look for the signal at ground level. A mag mount antenna or an omnidirectional antenna on the car roof helps a lot in this task. A max hold and a normal trace setup will also help quite a lot because you can sort of play hot and cold with the signal. See how close the current signal is getting to the max hold signal. Signal strength mapping will help on this. Okay. You also need to, another thing that's also very handy is to find a high place on a building top for direction finding. This eliminates many obstruction or multipath issues. Hilltops are your friend when it comes to interference hunting in a crowded area. As far as tools go, you want a spectrum analyzer that can measure signal strength. Important things for the spectrum analyzer are that it have a relatively fast sweep, it has a burst sweep mode, it has a wide RBW range and a high dynamic range. It's also important that the spectrum analyzer have signal strength tones. So you can put it on a particular signal, and as you swing your Yagi antenna around, you can quickly hear when you're pointed at the strongest signal. This can speed up an interference hunt no end. It's important to have channel power measurements, and the trace types I use are max hold, normal, and in some cases min hold. Min hold is particularly useful when you're dealing with a cellular uplink where the desired signal is normally bursty. And if there's something always there, it'll show up very clearly with min hold. Another thing that's useful is averaging, both trace average and video averaging. This is more useful when you're looking for a weak constant signal or CW signal that's nearly buried the noise. With today's digitally modulated signal, it's not quite as useful as it used to be. As far as antennas, my favorite is a Yagi. It has good directivity, a very good front to back ratio, and the side lobes aren't too big. It's very handy for hunting for signals. The downside about Yagis is they're frequency specific, and you generally have to have one for each band you're dealing with. Then there's a log periodic. Its big advantage is that it has a very broad frequency range. They're less directional. Matter of fact, I've been fairly frustrated with a few of them, and I tend to avoid them myself. They have more side lobes. The panel here is pretty broad, but the thing it has that really saves it, it has a very good front-to-back ratio, so you can screen out reflections quickly with it by turning it away from where you think the signal might be coming from to make sure you see the signal go down by the amount of the panel's front-to-back ratio. Okay. Here's an antenna accessory and interference hunter handle. It's something that Anritsu makes. It's got a GPS in it to find your current location. It's got a preamp. It's got a magnetic compass and a trigger. And this works with the mapping capability and the compatible spectrum analyzers to both locate your current direction and the direction you're pointing the handle. Then when you pull a trigger, it automatically puts a bearing on the map so you know which direction you're pointed. Now there's that little thing out there in front of the handle, and that's a series of filters that can be fastened between the handle and the antenna. And by the way, this handle will take just about any antenna with an end connector. Okay, it's a very useful accessory. Mapping on the spectrum analyzer is also useful. You see here 3 lines of bearing taken by that interference hunting handle. You also see some software. In this case, it's called Easy Map Tools that can find and prepare multi-level maps for the instrument. In this case, you can pan and zoom on the map and get the level of detail you need or desire for your interference hunt. That's good because you don't always know where you're going to end up when you are at the office getting ready to start. And this will make direction finding much easier. It's a lot better than a paper map and a ruler and a compass. I've seen guys out there in their trucks with their map spread out on the hood of their truck trying to take bearings to a signal. They've got their spectrum analyzer and the Yagi, and they're trying to hold the map down. The wind's blowing, and they're trying to use a compass, and they lay the compass on the hood of the truck, and that's a steel hood, and the compass isn't working so good. So it's a lot easier when you have the right tools to do the job. So let's talk about some interference hunting methods. This is a compilation of ones that I've worked with and that Steve Thomas has used. He'll be answering the questions for you later in this session. So here we go. The signal survey is a good way to find signals. It's where you seek the strongest signal. Here we show it being used indoor as a coverage check, but it can also be used outdoors in a geographic area to make sure that you drive around until you find the stronger signal. If you're in an area with a lot of multipath, this can sometimes be the only way to find a signal. It can be slow because there's a lot of trial and error to this, but it's also relatively sure. It's the most basic method, and it ultimately will work even in the confusing situations. Then there's successive approximation. A lot of people use these on the signal hunt. It's almost intuitive. The idea here is you have a spectrum analyzer with some tones, and you move your Yagi around until it's pointing at the strongest signal. Then you move in that direction, and you repeat. This works well in building. It works well outdoors. Works well for medium to short distances. It can be very fast. If you're trying to find things quickly over in a small area, this is probably the quickest way to do it. It helps solve problems with attenuation due to walls indoors. It can be misled by multipath. Okay. Another thing that helps when you're doing this is factoring in signal strength. You have to sort of keep track in your head of, oh, I moved in the direction of the strongest signal. I'm at my new location. Is this actually stronger than my last one? It can be a bit too much after you take 5 or 10 readings. You aren't going to keep too many of those power readings straight in your head. That is where a max hold trace comes in handy, by the way. Okay. Triangulation works good for longer distances, over say a half a mile or so. This requires a spectrum analyzer, a directional antenna, and hopefully it's got some mapping capabilities on the spectrum analyzer, which makes it a whole lot easier for everybody involved. And here's one thing I've noticed is many people are uncomfortable orienting a map to true north. And this avoids that issue completely because compass in the handle takes care of those issues. It doesn't really matter how you're holding the instrument. The map, the bearing line on the map will be true. Now there's some useful techniques as well with our interference hunt. Things you might want to know. If you're in an urban area, like the one you show here, there's often a canyon effect, okay? You tend to see signals just coming down the street. And Steve Thomas came up with a great technique for dealing with that, is you only take your measurements at intersections. You go to an intersection, you point your antenna down the 4 rows, the 4 roads, the 4 directions, and then you travel in the direction of the largest signal. You're using the canyon effect to your advantage here now. Eventually, you'll reach a place where the direction of arrival changes dramatically, and that means you're close, and you can use a traditional DFing to find the source in this case. Multipath can be a big issue, and a technique I use for multipath is shielding the antenna. Well, there's a couple. One thing I've used a lot is you can step behind a building, a shipping container, a large object. You can even hide the antenna behind your body to make sure that the signal's really coming from the direction you think it is, okay? So how you might do this is you point the antenna, the Yagi, in the direction of the strongest signal, then you point the antenna to the directly opposite that direction. The new signal should be smaller than the original by the front-to-back ratio of your antenna. And if that front-to-back ratio is, for example, 20 dB on a typical Yagi, the new signal should be 20 dB smaller than the one you saw in the strongest direction. If it's not, you're dealing with multipath. Okay? And there's some areas out here in front of the Anritsu offices in Morgan Hill where I can demonstrate that particular one. And you can be pointing directly at a cell site and get a measurement and point directly opposite the cell site. And the hills that are about half a mile away are beautiful reflectors. And you'll get a signal within 2 dB of your direct path signal. Okay? The second quick check is to find the direction of the strongest signal and step behind something solid. Again, the signal strength should go down unless you have a strong echo from behind you. This at least allows you to spot multipath. Knowing there's multipath there is half the problem. if you know multipath is present, you're halfway towards a solution. In the example I gave you, if I'm looking back at that bare hill, I know this area well enough to know there's no base stations in that direction, so I can pretty much arbitrarily dismiss it as an interference source. If I wasn't on a base station frequency, if I was hunting some unknown signal, though, I wouldn't know that, and it would indeed be trickier, and I might have to go find just where that multipath was coming from. The max hold and normal traces are very useful. As I mentioned before, I use it a lot. It's a handy way to mark the highest value measured while you move your Yagi antenna in a complete circle or step behind things or move the antenna 180 degrees to check for reflections. It helps when you try and say, is this signal the strongest one I've seen, or is the other signal the strongest one I've seen? Okay? You can also use max hold to monitor the total signal envelope. You see in the lower screen there, the normal is showing a signal that's changing both in power and in frequency, and the max hold is showing me the range over which it changes. This is a Wi-Fi signal, and we're seeing signals coming up on the 3 popular Wi-Fi channels in this case. The min-hold trace, in this case you can see the blue min-hold trace there that's always there, and the fact that there is a signal that's always there, while we have a WCDMA signal, it looks like, that's up on the top there coming and going, shows that there is indeed interference that's being masked by the pulsed uplink signal in this case. Burst mode, we've mentioned that before, and here we are always catching a Wi-Fi signal. It's going to spot the modern digital signals. It's quick enough, it's going to spot them every time and all the time. It makes direction finding much, much faster. It's a lot better if you can see a signal every time you look at it, every single sweep, instead of every 10th sweep or every 30 seconds or every minute. It speeds up these successive approximation methods no end. So here's the end game. Okay, once we get close, it's time to look around for potential sources. Rusty things, cell phone jammers, drifting TV remotes. What I'll do at this point is I start pointing my Yagi at things. I find out if I have a good Yagi that's in band, it's directional right up to where I'm touching the source. So I point my Yagi at things, older shared antennas, other radio transmitter, rusty things, houses, cars, cell phone jammers, whatever I think might be causing the problem. I've even walked up to a base station and pointed it at cables. There's a little bit of RF linking out of those coax cables that go up the tower, especially at the joints, and you can even identify what frequency those cables are carrying. It's a pretty handy tool. If you're finding a lot of rust, you might want to run a PIM test. Okay? One thing a PIM tester can do is measure distance to PIM, and it can find the distance from the antenna to an external PIM source, or an internal PIM source if that's what it is. And there's a lot of techniques here for dealing with PIM, which mostly boil down to get the rust out. Okay? Lightning arrestors tend to break down over time. They're important to have lightning arrestors. They protect the radio by arcing when the voltage exceeds a preset values. Over time, this preset drifts down. Eventually, the radio power can trigger the arcing. And this is classic impulse noise. It's intermittent at first and steadily gets stronger and stronger and becomes widespread across the system, especially if your lightning arrestors are all the same age. You're looking for a max hold trace raised 10 or 20 dB above the normal trace's noise floor. Micro-arcing can be caused by DIN connectors. The 7/16 DIN connectors, if they're over-torqued, then they're released. Then they're torqued properly, the two mating surface may not quite touch with enough pressure, or they're barely touching. And this can start causing small arcs that look a lot like PIM. And like the last example, this is intermittent noise, and eventually you're looking for the max hold trace just to come up 10 or 20 dB above the normal trace's noise floor. And it's very distinctive when you see this because you'll see the trace jumping up and down over a very broad bandwidth. So we know how to spot a raised receive floor. We know that interference causes receiver descents, and this is true whether the interference is on channel or whether the interference is mainly simply in band. We know that we need to know what sort of signal type should be out there so that we know what shouldn't be out there, and we should be familiar with the time domain aspects of our signal, including the spectrogram use. We know that we'll start out to find signals by spotting interference on a receive antenna, then moving to spotting it at the ground level, and finally locating the source by any one of a number of methods. And finally, when it comes time to fix and report, we're probably going to want to document what we've seen for generating a report and helping to resolve the problem. I know in some countries the results of these interference hunts are used for legal proceedings. In other countries, the results of the interference hunts are merely used to be persuasive. But at any rate, reporting is generally necessary at the end of one of these hunts. So there's a lot of other resources we have for interference, application notes, videos, webinars, and classes. There's a wide variety of them here, and these are online for your use. And I'm sure Steve Thomas will mention some of these during the Q&A period as well. We have a lot of video resources and webinar resources. So good luck to you, good luck and good signal hunting. And now I'm going to turn it over to Steve Thomas.
All right, thanks, Tom. As he said, we're going to get to the Q&A section, which we've had a number of questions come in, and for that we're going to bring in Steve Thomas, Senior Product Manager at Anritsu. So Steve, the first question we got in from the audience was, how can you do interference hunting on a low duty cycle signal?
That's a really good question. The way I've done it, it depends on what we mean by low duty cycle. If it's something that, let's say, is happening 1% of the time or more, the burst mode in some of our products will allow you to see it pretty continuously. It works very well. If you're talking about low duty cycle in terms of every once in a while it's there, something that's sporadic, I hate to say it, but that just takes patience. I helped track down an interferer to a cell site in San Francisco, and one of the things we knew was whoever had this improperly installed cell phone booster turned it off at lunchtime. So what can we do? When it got to be lunchtime, we had lunch and waited for it to come back. And if it's that sort of low duty cycle, that's all you can do. And patience may be in short supply, but you got to have it.
Okay, great. Second question we had come in is the receive pre-filter to clear out intermod from other frequencies?
Not exactly intermod. It could. It depends on the frequency of the intermodulation and how it's being generated. One of the questions that came through quite a bit was what is PIM, which is passive intermodulation. And if you have large signals out of band, the pre-filter will take care of those. But if those large signals out of band are mixing in something off-site or near the site and generating a passive intermodulation signal, that could get through because it may be within the band of the filter. So it's not a panacea, unfortunately. It's a big help, but not a panacea.
Okay, great. Another one is, so what are some techniques to identify a source without turning off all the transmitters? For example, if you're looking for an offender that is extremely wideband, greater than 1 meg.
Okay, that's a good one. One of the techniques that you may want to use is to use some fairly sharp filters, especially if you're at a very hot site, to reduce the number of signals that the spectrum analyzer has to contend with simultaneously. If you're at a really hot site, it may be hard to keep from having those signals generate intermodulation products even within the instrument. So eliminate as many of them as you can. I know that's easier said than done. I've driven past places where there were paging transmitters on a roof, and they were probably the worst offenders. I could hear them all over the place.
Okay, great. Which Anritsu product has the burst mode?
There's a couple. The MS2720T has burst mode. It was also introduced in the MS2720XC series a year or so ago. The MT8220T, which we recently introduced, BTS Master has burst mode. We'll continue adding it to products that have the technical capability to have it as time goes by.
Okay, great. Another one we had come in, we had a lot of people just ask about PIM. Can you just touch briefly on that and what it means and what it stands for?
Sure thing. PIM stands for Passive Intermodulation. It's basically the creation of intermodulation products by something that is not an active element, let's say in the output of a transmitter, let's say. Places I've seen intermodulation happen are PIM, a rusty picnic table, great PIM source, chain link fences. I saw one wonderful effort to introduce, or to reduce problems. A site that had a land mobile public service or public safety system and a cell site on the same hilltop. It was surrounded by a rusty barbed wire fence. I think somebody realized that created problems. So to try to solve it, they added some wires between the strands of barbed wire running vertically. Unfortunately, they used aluminum wire. So now we had some additional joints, dissimilar metal joints, and it was just a horrible sight. There were literally thousands of connections that could cause problems.
Okay.
Pimp, go ahead.
Oh, I was just going to say we have time for about one more question. So if you can you please explain how to DF in urban areas when all you can receive are multipath signals?
Oh, that's a fun thing to do. What you can do is just go to a once you're searching a problem and all you're getting is multipath, go to a corner, point your directional antenna down all the streets on that corner, figure out which way is the strongest, and walk that direction. I found this is best done on foot. Don't waste your time in the middle of the block. Just go to the next block, measure again, following the largest signal. Eventually, you will get to a point where when you get to the corner, the strongest spot may be behind you, or in some direction that's radically different than where you've been going. That means you're close, and at that point, you can start using traditional DFing techniques to find the solution. And I see one question that I'll answer very succinctly. Bert, no, it doesn't. Sorry.
Okay. All right, thank you. That's about all the time we have. I want to thank everyone for attending RF Interference Hunting Techniques presented by Anritsu. And just a reminder that everyone will be emailed a recorded version of this presentation. Our presenters today were Tom Elliott, Senior Product Manager at Anritsu, with help from Steve Thomas, Senior Product Manager at Anritsu. Thank you.